Okay, let us go ahead and get ourselves started. We're going to kind of pick up today with the whole idea of HVAC systems and really designing and sizing HVAC systems. And what I'd love to do is actually go ahead and start working with a very simple model of an HVAC system for a building and really look at how we can go through and use the model that we put together with ducts and basic fan units and registers, and go through and figure out how to actually size an HVAC system. So how we actually determine the heating load and the cooling load based upon the use of the space and some of the characteristics about the thermal zones and the boundaries. And then use that information to actually size a system that's appropriate for that space. We'll also go ahead and take a look at really how we can take the information about that building now that you've developed a lot further, and using information about the thermal properties of the different surfaces, take that into something called Green Building Studio to really understand where the energy is flowing through those different spaces. Now you can quickly evaluate a lot of different alternatives for going ahead and improving the efficiency of the building, as well as understand really where the potential is for some savings. So start to think about really, what we could be doing in terms of natural ventilation, to understand what we could be doing in terms of trying to generate energy in some alternative ways, as well as, just really, for wind turbines or from solar systems. Also think about really what the potential is for our building in terms of trying to generate things like water in other ways. Something that's very, very topical now, given that we're sort of suffering with a water shortage here in Northern California. Just really, what are some of the alternate strategies for either collecting more water or reusing some of the water in the building to minimize the load that it's actually creating on the utility system? Okay, as we dive in, or before we dive into all that, I'd actually love to share with you guys just a little bit about some of the stuff that is kind of currently hanging around out on the class community, because I think there's some really good examples from us all to learn from. And as I go through and do this, please try not to be embarrassed as I pull on some people's examples, because there's really some very good examples that I want to go through and share. Just really more as inspiration than anything to try and kind of encourage you all to kind of take a look out there and see what's available and see what we can sort of learn from each other. So I haven't been through some of the latest postings, but let me actually go back to some that are just a little bit older now. There's some really interesting stuff in there about some of the things people have been doing with the structural systems, things that CJ, that Sean have been doing, and that Christopher have been doing in terms of just actually starting to understand the structural system and some tips about how to approach the analysis. But I want to go back to actually, I'm going to go back to, let me see if I can find it. It's way back there now. Thank you all for posting so many good things to this. Yeah, there's just some really good examples, and CJ, I'm going to pick on yours for just a second because I think it's a really good example of this whole notion of just really sharing a model and the value of doing something like that. So CJ, Christopher, several people have actually been posting their models now to A360, and let me kind of show you what that actually does and why I like it when you do that so much, because it really does make it very, very accessible to us. At some level, when you post things to A360 and you share the link to it, we get views, the same sort of views that you've been creating, the views that are available in Revit. So you can look at the building elevations, you can look at the sections, the floor plans, things like that, and those are fine. Those are the static views. They're nice to go ahead and take a look at. They're very convenient for us because we can share those without actually having a Revit application. We can just do that directly from a web browser. But really where so much of the value comes is something like this. Within all these views, you can also go ahead and open something called an interactive view, and that's where it gets really interesting. So for example, CJ's posted this kind of nice view of the stairs and kind of looking through the main atrium space within the building. Let me switch that to an interactive view and show you what that actually does for us. And pop that up like that. So at this point, we basically have a lot of the functionality that's in Revit. So I can orbit around in the building, I can pan around in the building, and kind of move up and down through the space and start to explore the space in kind of a really cool way. And that's really just very, very powerful us as consumers to be able to kind of see the building and interact with it this way. So as opposed to sort of looking at just a few static views, you can actually pat around in the building and sort of see what it's like. So again, how we did this was we just uploaded his Revit model to the A360 site and just share the link, and from there you can go ahead and share these with other folks. So there's all sorts of cool views like that. If we take this 3D section view, which is also kind of a very nice one, and make it interactive, I can zoom on in there if I want to. And you can also start orbiting around and kind of taking a look at the model like in its detail. So it's just really a very great way to experience the building. Another thing we can do with this view is we could actually go through and view it on an iPad or an iPhone. So there's a lot of options for going through and sharing it. So I encourage you, as your building models are getting more developed, go ahead and post them to A360 and let us kind of experience them that way, because those little snapshots are great, but it's almost more interesting to be able to go ahead and pad around and like just walk through and see if you can sort of experience the building in a little more detail. So several good examples out there. I think what most people have been tagging them under is, just models to share. If you put them under and tag them models to share, they're easy to sort of first to pick out. So go ahead and see if you can. I've been trying to move things over to that category when they're there. Another, though, post that I really want to share with you, and I'll apologize because I didn't check this out in advance, is some of Sung Ho's presentations and what he's been doing with just some of the different views of the building, because I think they're really quite exceptional and quite inspirational, so I want to share those with you too. And if I go on down in there, just to sort of get a sense of really where he is with the whole building design process is really, I think, quite good and sort of nice to take a look at. One thing that I think is sort of especially interesting about how Sung Ho's approached the whole process is he's done an awful lot of thinking about the exhibits themselves, the spaces of the exhibits, and how people are going to be interacting with the exhibits. So I think there's some really good examples to look at within here. In that, the space is kind of rendered nice architecturally in terms of, the basic building elements, the beams, the surfaces, the textures are there, things like a little bit of the planting. But there's an awful lot of very interesting stuff within the design. For example, there's a green wall surface on the outside here, which is sort of labeled as green wall. And throughout the building, there's different examples of, we talked about the building could have features that are really illustrating sustainable design principles and how you can really feature them in the building. So, as we think about the building as a functional organism, that's super. As you think about it as an exhibit space and how people are interacting with the building, and make sure that as you're evolving your design, you're thinking about filling in the interiors and how that's going to actually be set up. You're starting to think about how people are going to be interacting with that space too. So within here, there's just all sorts of potential in terms of kind of rendering it nicely. But even in here, there's things that are sort of nicely diagrammatic about how the rainwater storage collection system is going to work. Or there's this notion, really kind of cool thing of there being a rainwater collection tank where even people from the inside of the building can sort of get a sense of really how much rainwater has been collected, over a certain period of time. Because I think it's sort of hard to visualize what that actually means and how much water that's actually creating. So just lots of different little examples of how you can go through and start to just illustrate the concepts and actually use the architectural design to do those. So if you can, go ahead and take a look at that one. That's another really good example, but go ahead and look at everyone's examples. The idea of community is really that we're supposed to be learning from each other. So please go ahead and take a look at what people are doing, and then based on that, use it as inspiration for your own design work in terms of how you're going to share and actually tell the story with other people. There's really some very, very cool examples out there. So please go ahead and take advantage of that community. Most people have been very, very good about posting things to the community. There's an awful lot of incredibly good stuff out there. If you haven't been posting very much to the community, please amp it up and put some work into that. That's actually a piece of ultimately how we're going to evaluate your project. It's not only how good your project is, but how much you've been sharing with other people and contributing to the overall community. So don't feel like you have to have an incredibly complete finished treatise that has everything fully resolved. Go ahead and throw your problems out there too, okay? Because you'll find out that a lot of people have been struggling with similar problems, and they may have some answers for you or some ideas about how you can tackle some of them. Okay, so take advantage of the community. Okay, let us then shift our attention. What I'd love to do is kind of take a look at this whole notion of the HVAC systems and kind of pick up on that thread, taking it towards building performance and actually how we can get information to help guide our continued design work. And to do that, what I'm going to do is I'm going to go on over to Revit, and I'm going to open up a model. If you want to follow along, add on coursework in the Session 15 folder, conveniently renamed from Session 14. There's now a file that you can download that will let you basically follow along. And if you want to, please do. Let me go ahead and find it out there. It is, where'd my coursework go? Looks like I probably lost it. So go on out to session 15 and download that file, the simple HVAC example. I'm going to go ahead and upload it or open it on this machine. Here's the basic idea. We've been going through and placing the basic elements of an HVAC system. We've been putting in some registers, we put in an air handler, we put in some ductwork, and tied these things into systems. And the cool thing about tying them into systems is as soon as they start to understand themselves as elements of a bigger system where all the loads kind of ratchet up and kind of feed into some main distribution or some handlers that ultimately feed the entire system, you can then go through and start doing some sizing. So let me go and I'm going to open this one. Head on out there towards 120B. We'll take a look at this simple system. This is where we left off last time. Go ahead and just over to the 3D view and we'll take it from there. Okay, so a very basic simple system here. We have 3 different supply registers, 3 different return registers, and air handlers is going to pump in air between those different systems. One thing that worked well about the overall system is that the systems were actually understood as having properties as a system. Let me show the system browser to kind of get a sense of that. I can do that by opening View and saying System Browser. That just gives me this view which shows the different systems right now. There's a return air system that has some components to it. There's a supply air system that has some components to it. And the nice thing about this sort of notion of this being as active model where we could go through and size things within this is that as the needs changed, as the loads changed, we could actually resize the system so that it was appropriate towards what we needed to handle the airflow. For example, in this system right now, which has been sized, this furthest branch out on the supply side, on the return side, excuse me, is actually smaller. And as we get closer and closer to the air handler, the ductwork's getting bigger and bigger. And the reason is there's increasing flow moving through. If I think about just this very last branch kind of hanging out here, this branch out here only needs to be handling the one register, which is the 500 CFM. As I move past this joint, it's picking up a second 500, so now it's actually picking up 1,000. And if I get into this joint, we're actually picking up all 1,500. So the ducts need to get bigger as we go through in order to be able to handle that increased capacity. So there was this thing called the system browser. Let's just go ahead and take a look at it. If I go through and I choose the system, I can tab to choose the entire system. You can get this thing called the System Inspector, which lets me inspect a system. And inspecting works like this. I can go through and just hover over any piece of ductwork, and it'll show me the flow on this is currently 500 CFM. There's 1,000 flowing through that duct, 1,500 flowing through that duct. So we're actually getting a kind of sense of how these things add up. And what will happen is as we go through and change the loads, okay, we can resize those things. So for example, if for whatever reason this turned out to be, as opposed to be a 500 CFM register, if I actually needed to get 1,500 CFM through there, I could apply that. Okay, things don't resize automatically, but if I now choose that system, and I'll go to the, I believe it's the Systems tab. Or is it the Analyze? I never remember. I'm going to the duct size calculator. That's a multi-select there. If I can get that size. Duct insulation, modifying the ducts. Where did the calculator go? I always have trouble in terms of finding things. That's the lining, that's the insulation, that's the selection of it. Let's try selecting it over there. Oh, it's because I'm still in the system inspector. Let me cancel out of that. That's going to kill me. Okay, now I get duct and pipe sizing. I knew it was hiding there somewhere. It's because the inspector was still open. If I say duct and pipe sizing, I can choose whatever criteria I want to go through and use, whether I'm going to optimize for the velocity or the friction that's produced. I'll say OK, and you'll see what happens is it'll go through and do a little resizing for me. I thought it was. Let's see what it's got. Oh, that's 500. That's 500. That's 500. I could swear that I changed that, but if I didn't, I will apply that. Okay, you're truly 1500. That looks good. So now, choosing that, I'll use the duct and piping calculator. Say OK to that. It's going to go through and evaluate all those ducts, and you'll see it actually upsized the ducts quite a bit. So now that's actually quite a bit bigger. That needs to be like a 15 by 15 duct or something like that. So this branch needs to be very large because it's carrying at 1500. Here it's gaining 2000. This little branch over here doesn't need to be so big. That's only handling 500, so it can be quite small up to that point of juncture. Okay, so you can go ahead and do this sort of simple sizing doing things like this. And that's kind of cool. But let's talk about now the next step, which is really how we actually go through and size actually the heating system that's going to drive all this. Because we have all this air moving through. That's cool. We need to have the air moving through for just kind of safe ventilation. But now we need to maintain kind of the temperature that we want to be in this building, either using heating or cooling and all the considerations about really what's going to drive it here. So let's turn our attention to that and how you do that. So the whole notion of heating and cooling, it really starts with the idea of where we started at the beginning of this quarter. It's the project location. Based on that project location, there's a temperature profile. And based on that temperature profile versus the temperature we'd like to maintain in the different spaces, we're going to heat or cool the space to try and maintain that. Okay, and that's going to be affected very radically by just the surface materials and what the thermal properties of those things are. So it all starts with this notion of, under the Manage tab, if you want to go there, just choosing the project location. Currently it's set to Boston, Massachusetts, so if that is appropriate, we can leave that there, but we said we were going to change it more to be, if we were going to look at our building in Stanford, California. So we can go through and set a location that'll actually then determine what the temperature profile that's going to be associated with this building is. Another thing we need to do just to get going with this whole exercise is if you go to the Architecture tab, we're going to use a concept which is similar to rooms. It's called spaces. And spaces, in many cases, map to rooms. Sometimes spaces don't map to rooms. It really depends on whether there's hard walls and all those boundaries. Spaces are really conditioned spaces, or spaces that are all going to share the same thermal characteristics. Okay, so that may or may not line up with room boundaries. Okay, so in order to go through and work with spaces, we're going to go through and place some spaces. But even before we do that, I'm going to go through the area and volume calculations. That's under room and area. And turn on this notion of we always want volumes to be computed. Let's talk about why that is. Typically, when we go through and calculate areas, we're just looking at the 2D space. It's very, very quick to do length versus width and get a quick number that way. Volumes are necessary when we start thinking about air movement and the total amount of air we're flowing through the space. So we're going to turn that on. It's turned off by default. Turning it on starts to consider the height to the ceiling, the height to the roof, and the volume, which takes a little more space or time to go through and calculate that. So that's why it's turned off by default. But we're going to say areas and volumes. Say OK there. Now we're ready to go through and put some spaces in here. Actually, there are some spaces already placed here, just so you can sort of get a sense of them in this model. I did go through and put a space over here. There is a space for what I'll call the workroom, the main space over here. There's another space over here for the storeroom. Okay. And in that space, we can go through and set different characteristics for it. We can, for that space, go through and say that in terms of the lighting calculations that are going to be done, really what the work surface is that wants to be computed, so typically about 2'6" off, or about desk height. Really what the reflectance values of the floor, the ceiling, and the walls are. Notice ceilings tend to have a very high reflectance because they're often white, and we like that light to reflect on down there. We're not going to put anything in about the electrical loads right now, but in terms of the mechanical flow, you can actually see that, oh, the actual supply airflow 1500, actual return airflow 1500, that's based on the registers we've actually placed in that space. So it's doing a little tallying of what's going on right now. And we'll go ahead and figure out what that specified supply airflow is in just a minute. Okay, so we're going to have a workroom, an area space over here. We're going to have this other space over here, which is a storeroom. I'm going to show you placing spaces. It's actually pretty straightforward. I'll just take this one out so you can see it. I'll take that out. What I'm going to do is just under, hang on, is it under analyze? There it is. Spaces. I can say I want to put a space in there, and then we'll start to have those characteristics. So different spaces, you need to create spaces. Spaces are going to be, not exactly zones. They're sort of thermal spaces. The second concept you need to know about is zones. Let's talk about zones. Zones are really kind of a collection of spaces. Yes?
Would you make zones like that are like 5 feet tall and then the rest of the rooms? Is it like, or sorry, spaces, if you want to know like occupied space or and then the space above it?
Oh, actually, no. What we tend to do with the spaces is we'll let that go all the way up to the ceiling plane, wherever that is.
Mm-hmm.
Yeah, it's interesting to sort of think about sort of subdividing in terms of this space versus that space. Since there's no real boundary between them all, I'm not sure we can really get much useful data out of that.
Okay.
I'd probably just let it run all the way up. Although what we'll tend to do is, if you have a plenum system, the plenum will be a separate space than the room.
Okay.
And then let the mixing happen within that. Okay. Good concept though, but I'm not sure if the model will really do much with it.
Okay.
Okay? Okay, next up is this notion of zones. Let's talk about zones. Zones are based on this sort of notion. Zones are really just collections of spaces that are essentially going to share the same, what is it, I think I'm sharing the same thermostat. It's going to have the same set of thermal controls. So for every zone, we're going to choose what the comfortable cooling set point is, what the heating point is, and often zones are made up of several spaces put together. They don't have to be. You could have, in some buildings, you could have every space have its own separate zone that would have its own separate thermostat. Okay, this building tends to have that. We have these separate thermostats in each individual room. But if you want to have a collection of spaces that are all tied together on a single thermostat, okay, then you make a zone out of them. So in terms of zones, let's take a look at that. Zones are really all about, see if I can kind of edit the zone. I'm just going to go through and collect different spaces. So I have a space over here. I'm going to basically add that space into it. So I should now have a single zone. Let's see if I can kind of actually select it. That's the space. That's the space. I want that to be, let me edit the zone again. Let me do this. I'm going to take out the zones first, because I think when I eliminated the first space, I sort of messed that up on you. I'm going to choose everything, do a little filtering. Yeah, I do have to have 2 zones in here, which is going to confuse it. Let me check none. I'm going to get rid of the zones so I can put them back in again. So I have 2 zones in that room. Okay, so what I'm going to do is grab that space, come on over and say that I want to create zones. I'm going to edit the zone. I'm going to add that space into it. Okay, now they're together. You see that there's actually this black boundary that goes around the entire thing. So this collection of these 2 different spaces is going to be a single zone. Zones have these properties. They have this notion of kind of the cooling information and the heating information. So in a zone, we can go through and say that, hey, there is a cooling set point and the temperature of the air that's being used for cooling. So for example, if we want 74 degrees to be that target temperature, if it gets any warmer than 74 degrees, go ahead and try and bring it back down to 74 degrees. Okay, we can leave it that way, or we can change that temperature. So if we want to change the thermal performance, we could change that to 76 degrees or whatever you think a valid temperature is going to be. Same thing on the heating side. On the heating side, the heating set point is set to 70 right now. If we're using too much heat, we can actually lower that down to 68 degrees or some lower temperature. because really that temperature is going to be used to drive really how much heat we need to supply for the building. Let me finish editing that zone. We are in pretty good shape in terms of what we need to do. So the next thing we're going to do is actually go to this fabulous little wizard that helps us compute heating and cooling loads. And it's under the Analyze tab. It's under the Reports pane, and it's heating and cooling loads. Let's take a look at that. Within this wizard, you actually get a very high-level view of really what it thinks the building looks like. And this is what the building looks like in terms of there being two zones, or two spaces. The space out here, the space over there. We can see it's in Stanford, California. We can say something about the building type. That can be saying something about what the approximate number of people per square foot, what the amount of heat they're generating is, what the hours are. Okay, so we can go through and choose different types of buildings. I'll leave it as office, or we might change it to museum if that's what we're thinking of for our space. Okay, you can also say a little about really what is the type of the system that you're imagining in there right now. Whether it's a kind of forced convection heat, whether it's a variable air volume system, whether it's a radiant system. You can start to put in our constant volume in there. A water loop, some sort of split system, active chilled beams. There's a lot of different systems in there. Look at it's going to turn out for what we're doing right now. What is it? In terms of generating the amount of heat or cooling, it's not hugely sensitive to that. In terms of what's going on. Later on, it'll be important what we choose in terms of how efficiently we're providing it. But we can probably leave it at the default assumption for right now. Okay, if you want to get into the details, you can take a look at that and sort of say there's an overall building model. It's made up of two different spaces right now. There's this space, actually, that's interesting. That's two different zones. Okay, we're going to analytical surface. Try that first. Okay, so here's the different surfaces that it considers to be the floor surfaces, the wall surfaces, the roof surfaces. And they're kind of color-coded in there. This bothers me that there are two different spaces in there. Is that sort of looks a little suspect to me in terms of what's going on. And what's this one telling me? He's not bounded by a roof. Okay, a ceiling. Okay, that doesn't look very good in terms of what's going on. So before we go off and try to analyze all this, again, it says the space is not placed. Okay, well, that makes sense. It looks like we had created some spaces. When I took out that space, it sort of messed up the model. So let's go ahead and do this properly so that we can just get this all looking well. Okay, so what I'm going to do is I'm going to go to, there's a space schedule. Okay, and you'll see there's three different spaces over there, and that's part of what's messing us up right now. Let me delete this row. Delete that row. I'm just going to start this over and make it a little bit cleaner for you. Okay, no spaces right now. Might be a little bit better. Okay, so we'll come in, we'll put in a space. The space is over here. It's only going up to level 8 feet right now. To your question, Amy, okay, we should go ahead and make sure this is tall enough so that it actually does hit the roof. Okay, we want it to be enclosed at the top. So I can put in there 10 feet, I can put in there 12 feet. I just need to be tall enough that it'll intersect either the ceiling or the roof element. Okay, next up I'm going to put a space over here. Okay, so let's see if I got it right. That one needs to be 12 there. That one needs to be 12 there. So I have spaces 6 and 7. Let me rename them just so I actually have a little more idea of what I'm going after. Workroom right there. And storeroom over here. Okay, got my two spaces. They're looking pretty good. Just to be certain, let me just check the space schedule. Okay, workroom and storeroom, looking good. Next up, I'll tie those two things together into that zone again. So I'll choose one of them. Go to Analyze, and I'll say let's create a zone. So I'll add this one in. Let me edit the zone. Okay, now it's all one big zone. Okay, beautiful. I think we're in good shape now. We don't have any loose hanging ends. If you get to one of these reports and you see all these like loose hanging ends, watch out for that. That's a pretty good idea that things aren't going to work out so well. Okay, it looks like there still is. Let's see what's going on here. Those two are in there. Zone 3 is just kind of messed up here. I wonder if I can get rid of it over here because I don't, or space 3. I want to delete that zone. It's not active right now. Okay, let's see, because it's zone 3. Cancel out of there. In terms of the spaces are there, but can you schedule zones? I don't think you can schedule zones, can you? Yep. So I got the space schedule. Let's even here go ahead and can I put the zone in there? So I can see they both belong to that same zone. I have this mystery zone left over. Let's see if we can actually get rid of it. Another way to do it would be back over here. I'm going to try this again where we do the selection. So there's the two zones. Okay, I got the two zones right now. I'm going to take out the two zones. That sounds really, there's got to be a better way to do that. I think if I did a lot of careful selection, I'd do a better job with that. But I'll say, let's do the zones. Let me go ahead and get that one. Actually, canceling the zone. What I usually do is I choose the space first. Actually, I should make sure that I didn't mess it up again. Okay, filter. The zones aren't there yet. Woohoo! Okay, we're in better shape. We got the space. Okay, we'll say that we're going to analyze it. Make the zones. The first one's in there. We'll edit the zone. I'll add in the second one. Okay, now we're good. Finish that. Okay, a long-winded way to get there, but hopefully we're in better shape. That's looking better. We have one zone that has two different spaces in here. Okay, that's looking sort of the way you would like it with no little warning signs in there. So once you've gone through and created a zone, here's what you can do. Is for each of these different spaces, you can say a little about what the type of the space is. Right now, space 6, the workroom, is really defaulting to just the same building, or the same as the main building type. So if I leave that set to building, it's going to have the office functionality. Okay, and whatever is assumed to be happening in that office. The storeroom is also defaulting to building, so it's also assuming office. If you want to get a little finer, you can go through and start to change it to say that, hey, the storeroom really has a different functionality. It won't have as many people, it won't have as much heat generated. And to do something like that, you can choose the little menu and really say that, you know, this is really not so much an office area as, oh, some sort of storage area. Like stacks in a library, some sort of inactive space. Office enclosed. Certainly not an exercise area. Let's say active storage. Okay, so we can start to change things around a little bit in terms of not only what the functions of the rooms are, we can actually start to change around the construction of the building itself. Let's talk about that. The building right now is assumed to have some different properties. It has actually fairly weak thermal properties right now. The roof is made of 4-inch lightweight concrete, which has a pretty high U value. The slabs are uninsulated solid slabs. The exterior walls are concrete block. Again, have a fairly high U value. Even the windows and the doors. So the windows are large double glazed windows. The doors are metal doors. There's a series of different things that it's sort of computing right now. And we'd actually like to go ahead and improve on that a little bit. Okay, so what we can do is as follows. For the building itself, go through and start to change the overall construction a little bit. So for example, if we want to say that for the purpose of our calculations, the roof isn't something that has this very high U value, we can go through and change that. We can say that, you know, I would like to go through and choose a higher value construction. So, like an R38 wood roof frame roof, or an R30, or just some sort of thing that's going to have a much lower U value. You can see that the current default U value is 0.22. If we put like an R30 roof, it would be 0.02. That's going to have a huge impact in terms of the amount of heat that's going to be flowing out there. Okay, actually, let me do this. I'm going to leave the default assumptions first. And we'll see how bad the system would be sized, or how massive the system would have to be with those default assumptions. And we'll change the assumptions so you can sort of see what the effect is in terms of just the overall sizing of the system. So for a starting point, let's just leave it as default. Okay, and from that, then we'll go through and try and improve it. So I'm just going to cancel out all that. We're looking pretty good. I basically have my zones. I'm looking pretty good over here in terms of my default assumptions in Stanford, California. What I can do is actually just say calculate. Okay, and let's see what it actually comes up with. It's actually the second one that came up. Okay, this is one we just calculated. Let's talk about it. Here in Stanford, California, the latitude seems to be 42.21. The longitude, we have some ideas about the wet and dry bulb temperatures. We can take a look at the office building being about 2889 and the volume of the building. Well, let's kind of go scrolling on down here and see what we can sort of figure out here. Okay. Within this building, okay, there's a couple of kind of key things you need to pay attention to. For the calculated results for this two-space building, there's a peak cooling load and there's also a peak heating load. Okay, so 85,000 BTUs on the cooling side, heating side 68,000 BTUs. Okay, there's also a peak heating airflow both on the cooling and the heating side. Okay, so there's two different sort of things going on here that you have to sort of watch out for. One is the peak cooling or heating load. That's going to actually help you size the system. So how big the actual chiller, the actual heating plant has to be to go through and kind of keep it within the comfortable temperatures that we specify for the building. The other thing you have to watch out for, though, is just this airflow. So the heating airflow or the cooling airflow, that has to do with basically how much air we have to move in order to deliver that much heat through the space. Okay, so for the heating side right now, we would require 2266. I think we only have 1500 in there right now. So we'd actually have to add more registers to go through and deliver that kind of heat throughout the space if we wanted to actually maintain it at the cool temperature. Yeah, or at the heating temperature that we wanted. If we didn't put that in there, we could have an oversized heating plant, but it wouldn't actually be able to deliver the heat, so you'd still have cold spots. So the two things have to sort of work together. So if you scroll on down there, it'll summarize it by zone. It'll actually talk to you a little about also, really what's going on in terms of where the load is being generated. You'll see that right now, of all the different components of the building, most of the cooling load is coming from the roof. And most of the heating load is coming from the roof. So if we were going to think about trying to improve this building, the roof seems to be an area where we can make a pretty huge improvement as far as what's going on. Power, in terms of the consumption, we can't really do much about that. The people, yes, we're actually computing, kind of interesting, about 3,600 BTUs is just for the people that are actually in the space and what we're actually going through and generating. Okay, but where does that fit relative to the walls? It's actually, walls aren't really all that very significant. Right now we have nothing for the windows. That's because the space has no windows right now. Well, a little bit related to the door. We have a metal door. We can start to improve on that. But you can start to see for these different spaces, really what the heating and cooling loads are, and then what the volume needs to be. So to keep the workroom, we need 71,000 for that, and we would have to have about 3,400 with the ventilation. For the storeroom, that active storeroom, it's about 12,000 and about 550 in terms of what we need over there. So at a high level, you can start sizing up a system using this thing. Okay, but you don't necessarily want to accept all these default assumptions because the default assumptions are pretty lame in terms of the type of materials you might actually put into this space. So let's go ahead and rather than accepting all these default assumptions, adjust the values to be closer to what we really think the building will be that you're putting in place. Okay, so here's how we're going to do that. We're going to go back to that old heating and cooling calculator. And we're going to take a look at these details Actually, it's of the building right here. Let's kind of change these a little bit. Okay, so as you think about your buildings and the roof that you're likely to put on your building, you know, what sort of R value are you imagining for your roof? Do you have a sense of really what the R value might be?
30s.
Probably in the 30s. Like just in residential construction right now, anything in California right now for this zone, we need to put pretty much an R30 roof on it. Okay? If we were up in Lake Tahoe or a very cold weather climate, we'd have to put at least an R38. What I'm doing is I'm thinking about prescriptive standards that are part of California's Title 24 Energy Code. Okay? They're the easy way in terms of getting some general guidelines. You could always go through an engineer, something that has higher or lower values, and be very precise about the amount of heat that's flowing in and out to that surface. But if we were looking at for the real simple answer, they'd say, oh, you're putting a roof in Palo Alto? It should be R30. Okay, if it was a colder weather climate, it might want to be R38. So if we just change that, for example, to another material, and it really all comes down to the U values, which are sort of just the inverse of the R values. So we have metal sheathing with different types of concrete with R19 insulation, R19 wood frame deck. The truth is, it really doesn't matter which of these we choose in terms of how it's described here, as much as what the R value or the U value is. That's what's really just being used in the calculation. So if you find something that has the right R or U value, go ahead and use it. And just in terms of relating those two things, what is it? 30, 1 over 30. It's pretty close in terms of what's going on. The basic relationship should be that U is equal to 1 over R, R is equal to 1 over U, something like that. They kind of invert themselves that way. So if I went for like an R30 roof, let me put that in there. Okay, I could mess around with some of the other surfaces in here. Oh, I could go ahead and mess around with those exterior walls. Those exterior walls really aren't that insulative right now. If I want to put like an R19 wall in there, which is again sort of a fairly standard wall type of construction we put in Northern California, I can go through and look for something like that. So I'm going to go pop it on down there, see if I can find some nice frame wall. Brick, lightweight concrete. Like an R19 wood frame wall. Super. So I'll just leave it at that right now. We won't necessarily insulate the slab. Other things like if we put some windows in here, we can start paying attention to what the window values are. But just by changing those two values of saying that you're going to insulate those two things, let's say okay to that and see how big a difference it makes. Okay, so I'm going to recalculate. Okay, let's go back to 2 for a second. Where we were before we started changing things around was, I'm going to find that table that actually summarizes it very neatly. There it is right there. Actually, I can do it up top there too. Hang on. I'm looking at 3, not 2. There we go. I could tell the values were too good. Okay. Next. So cooling right now is going to be 85, 164. Okay, with a flow rate that we have to go through and put in a 3910. Heating, on the other hand, is going to be, where'd it go? Heating, peak heating, 68,684. With a flow rate of 2266. Okay, that's our kind of dumb assumptions. Let's take a look at the smarter assumptions. Okay, peak cooling load, what is it, 38,000? 477, I'll call it. Cooling airflow, 1722. Okay, let's go through peak heating load, 17. 274, 570. Okay, and that's really with a combination of R30 and R19. In terms of sizing a heating or cooling plant, pretty significant difference in terms of what's going on. So here's my caution, or here's what I really want to sort of drive home about this whole calculator is, if you're going to use the calculator, go through and make sure you sort of get the assumptions to be fairly close to what you really want in the building, because it can lead you to something that's almost 3 times off if you just kind of use the default assumptions. So go through and just with some very simple things about really what the R values are, get you much, much closer to what it is. Okay. Now, this calculator, it works very, very easily. It's kind of simple about what it does, and it can keep track of your building, or kind of up with your building very, very nicely. So for example, I'm going to pop in over here. And so far this building's been pretty boring. It doesn't have any windows. It doesn't, it's just basically like a big old box in terms of what's going on. If we go through and start changing this around and enhance our design, so for example, I'm going to cut out a little corner of that wall. I'm going to cut away a corner of this wall. And just say that these 2 sections of the building over here are, for example, curtain wall. Just to add a lot more light in there. Okay, that'll again should have a fairly big impact on the building. Let's go and see what it actually does. So as I go through and I add in all that curtain wall over in the corner, let's just go back over to Analyze and take a look at what it does. Reports, heating and cooling loads. Okay, not looking too awfully bad in terms of what's happening over here. Let's do a calculate. Okay, we're in load 4. So with the curtain wall now, it's what, 46? And for the cooling load, that's cooling load up top there. The heating load is 32. Okay, in there. And what's happening to capacity? The airflow is 1,000. The cooling capacity, latent load. Airflow, 2107. So what's the message? It's like, it really is pretty sensitive. What'll happen is as you go, refining your building design, you'll start narrowing in on something that's pretty close. Even from 38 to 46, that's not nearly as bad as like the nearly 3 times it's coming over to here, or something like that, or 2.5 times. But as you continue to refine your building and change those assumptions, you get a finer and finer sense of really what the actual heating and cooling loads will be. And the further we go with all this, the better and better an answer we will get in terms of all that. Okay, any questions about sort of sizing that stuff? It's really, it's sort of black box about what it's doing. What it's doing is it's really the same exact sort of energy analysis that you've been doing in eQuest or in any of the tools in Green Building Studio. In fact, we're going to go ahead and show you how it all relates back together now. But it's the same basic calculation. You've got surfaces, you have a certain amount of heat that's flowing in and out of the surfaces, you're trying to maintain a constant temperature, or at least a comfortable temperature within a range inside of a room. So, as we sort of change the percentage of the different types of surfaces and the thermal properties, just the loads are going to go ahead and adapt themselves accordingly. So, with this information, if, for example, we said that it was going to be 1,072 on the heating side, we're fine. On the cooling side, if I really need 2107, I probably need to go back and add in some more registers, to this little building to go ahead and handle that. So if I'm going to go through and have that, what I really need to do is back over here in my little 3D design, I need another register in there to go through and actually get myself up to the 2000 or 2100. So I might need to kind of copy that over. And after I go through and do that, basically see if I can connect that into. That was actually kind of a messy one because it put a hard duct in there. It'd be much, much better 40 feet. That must be left over from last time. Okay, about 10 feet off level 1. So systems, put a duct in there. Don't click around randomly. It's interesting, that doesn't quite understand that it's return air yet. Now it does. And the final thing is I should put a little piece of flexi duct in here. So the system will be a little bit better. Okay, we need to do something similar on the return side too, or the supply side, so that we can go through and kind of pair them or have them balanced.